a lot of people think that life is about prediction, and predicting the future is the fundamental thing that life does. And I think life is actually about constructing the future. It's a much more active, like physical structure. And so AI algorithms are trained on huge volumes of patterns, and they can predict features of those patterns, but it doesn't mean that they're actually actively constructing their patterns. They're responding in kind of a way to an environmental stimuli to try to predict them. So, and this gets into the ideas of like, is AI creative or not?
Welcome to Closer to Truth. I'm speaking with astrobiologist and theoretical physicist Sara Imari Walker about her groundbreaking new book, Life as No One Knows It, The Physics of Life's Emergence. Sara, it's great to see you. I've been looking forward to our conversation for a long time.
I am thrilled to be here. I love all your work, so it's really exciting to finally have a conversation.
Great. Well, let's start with a really big question, kind of an overview of your views, and then later we'll obviously get into a lot of depth. How are you changing, as your book presents, the approach to whether there is life in the observable universe, and if so, what kind of life?
Yeah, so my approach to the problem has really been to focus on whether there's windows into fundamental physics by studying living things. So traditionally in my field with people studying the origins of life, they've been really focused on trying to define life by properties we might observe for life on Earth, like has metabolism or is a replicating system. And my feeling always was that if we wanted to find life on other planets and we really wanted to solve the origin of life, we really have to understand the transition from non-living to living things, and that physics might be quite deep and universal. And so what I've really been focused on most of my career is trying to understand the role of information as a fundamental category of nature associated with causation and what that actually means in terms of the physics of life. And if that could help us actually identify alien life and also solve the origin of life. And that whole journey has led me to co-develop a theory called assembly theory that I'm really excited about, which is basically a conjecture that life is the only mechanism the universe has for constructing complex objects. And we have ways of formalizing that. And then it has some really interesting implications for concepts of time and what we think about as sort of the fundamental structure of life and what kinds of possibilities there are for life in the universe.
Yeah, that's great. I'm looking forward to all of that. And you deal with the three big questions: the origin of matter, the origin of life, and the origin of mind or consciousness, which is, of course, all of which are closer to truth core topics. So we can talk for about a week. But it all is a unified package, the way you present it, which to me is very exciting.
Yes. I think when you think about really deep fundamental problems, you start to see that they're all connected in a rather deep way. So I think once you're working at the sort of level of description of the physicist's conception of nature, it's actually a really constructive exercise to start seeing connections between things.
Okay, well, we'll listen to that, and we're going to challenge it too, as you would expect.
Excellent.
But first, let me give a more thorough bio, which you richly deserve. Professor Sara Imari Walker is an astrobiologist and theoretical physicist, as I've said, with research interests in the origin of life, artificial life, and the detection of life on other worlds. She is deputy director of the Beyond Center for Fundamental Concepts in Science at Arizona State University, working with Paul Davies, our long-term Closer to Truth contributor and good friend. She is also principal investigator of an important NASA astrobiology research project focused on planetary systems biochemistry, which is providing a new set of tools to identify signs of life. Her PhD in physics and astronomy is from Dartmouth, where her doctoral advisor was Marcelo Gleisa, a recent Closer to Truth contributor. So, speaking of Marcelo, you quote his three hard problems of existence, as we've said: the origin of matter, the origin of life, and the origin of mind. Can you just kind of enrich that combination of the three origins?
Yes. So I was very lucky to have Marcelo as a PhD advisor, getting me interested in big questions early on. It was one of the reasons I was excited working with him. And I think his articulation of these hard problems was, really enlightening for me. I focused most of my career on the problem of life, which people have not traditionally thought of as a very hard problem. So I think we're more familiar with thinking about the hard problem of consciousness because that's been popularized very heavily, which is this idea that we can't explain with current scientific tools subjective experience. And if you get into those kind of philosophical debates, it becomes very clear that we really can't talk about the properties of matter outside of measurement either. So there's this introduction of this idea of a hard problem of matter. So the hard problem of matter is about the idea about what we can actually measure about material objects in the universe. So if you think of an electron as an example, we actually don't know what it's like to be an electron. Independent of measurement. So all the things that we know about electrons are about regularities that we measure with respect to measuring devices. And so it's when you start to look at, what we define as matter and how we actually come to understand what material properties are, it seems that the hard problem of consciousness and the hard problem of matter are actually very similar. And so I was thinking about this problem quite a lot in the context of thinking about the nature of life and this idea that a fundamental property of living things is that information is causal, and that there really is an associated hard problem with life in the fact that we actually don't know how abstract properties could be causal categories of nature. So we have these kind of dual problems where we don't know how to define exactly what is material. And then on the other side, we have these informational things that seem causal. And so to me, it seems to suggest that we perhaps don't really understand the material substrates underlying what physical reality is. And that's sort of how I lead into thinking about theories of life as actually redefining some notions of what we consider to be material.
So this is really important. The traditional thinking is that the three problems you articulated, matter, life, and mind, are indeed three of the fundamental questions, but each one has its own sort of approach to it, and there isn't the kind of underlying unity as sharply as you're drawing it. So, for example, the questions of the origin of matter, what matter is, that deals with the category of foundations of quantum physics, which we deal with a lot, and that's done from that. Information is one of the ways that that's considered, but there are lots of different ideas and different approaches. Similarly with consciousness, which is probably the clearest example, as you've said, of a hard problem, because how can you get sentient, how can mental states be derived from physical brain states, is to put it away, as you said, subjective experience. That seems to be clear. And with life, traditionally, it does not have the same kind of uncertainty because, as you said earlier, there are definitions of metabolism subject to Darwinian kinds of evolution, reproduction that seem to explain life so that it wouldn't be at the same level of uncertainty that we find in the foundations of quantum physics and the hard problem of consciousness. So you're in essence contradicting that traditional approach. And so I'd like to, push you a little bit more on that.
Yeah. So one of my inspirations on that was thinking about, in the hard problem of consciousness, people will talk about the neural correlates of consciousness. So even if you understood the functioning of the brain and you could, map all of the, wiring and firing of all of the neurons and understand all of the mechanisms, how the brain works, you might still not be able to answer the problem of consciousness.
Right.
Exactly for this reason that, it's related to the measurement problem and how do you understand what it's like to be something internally when you always observe it from the outside. And so I started to think about some of the properties that you're talking about, a self-reproducing molecule or a metabolic system or like a cellular architecture as chemical correlates of life. There are things that, are what we observe when we see living matter, but they may not be the fundamental essence of what it is to be life or alive. And I draw some parallels in the book. I've thought a lot, actually, in my work about the history of measurement and what we take to be physical. So it's super interesting to me trying to come up with new theories that we take things like mass and electric charge as being real physical properties of objects, and we just assume that like they're just objective features of the world. And we forget that when we were developing theories in physics, we had to invent the technologies to do precise measurements of, seconds and precise measurements of mass in order to come up with the laws of gravitation, for example. And so all of these laws are actually built on things that we have gone in the lab and empirically measured. And the challenge with life, I think that's very hard is, and why I think it qualifies as a hard problem, is that everything on this planet is the product of evolution. So the very phenomena that we're interested in studying, the nature of life in the universe, is literally constructing everything on this planet. And so if you think that information is the sort of fundamental essence of life and it's propagating through living structures to generate new kinds of objects or new kinds of biological systems and technological systems, everything we do is kind of imparting that physics into the substrates. And so this issue of the chemical correlates, I think, actually becomes really quite hard, because what has been a tendency in my field is to say, we find proteins in living things, or we find DNA in living things, or RNA. And therefore, if we make the parts of those prebiotically, we've solved most of the origin of life. And what we don't realize we're doing is putting a ton of informational constraints and basically purposeful goal-directed behavior toward those molecules in this vast exponential space of possibilities. And it's because we don't really understand our horizon as, where are we evolved into as far as what the universe could create, and how big is the possibility space somewhere else if different informational systems emerged that could construct different possibilities. So I think that this sort of issue is very nuanced. Of course, we see physical structures that we can measure with current technology as being features of life as we know it, but we don't understand the deep principles that allow us to anticipate life as we don't know it.
Okay, so you've now used information several times in a foundational sense, and this is a fairly new idea, that not terribly new, that is developing, that information is not just a way of describing the physical, the ultimate physical substrate, but in fact is. So it's reifying, it's making information a thing rather than a process.
Right.
And sitting fundamental. And this is, of course, controversial, but I want to understand, is that a fundamental assumption of the work that you do?
Yes, it is. And it has been since sort of the very beginnings of when I started thinking about the origin of life. And of course, you're right, there is a long tradition of arguments made in favor of information somehow being the fundamental substrate of reality. So there's obviously Wheeler's famous "it from bit" and Landauer's famous phrase, "information is physical." And I think a lot of that tradition really came from this sort of idea of reduction in uncertainty that came from Shannon information. What I was always interested in, and Paul and I, Paul Davies and I actually wrote a paper on this when I was a postdoc, when I first arrived at the Beyond Center, which was on this idea that information is actually a causal category of nature. So it's not just, like a way of describing the fundamental layer, but actually like information can emerge in the universe and cause new things to happen. And this has been something that I thought was very deeply intrinsic to what differentiated life from not life, because it seems to me to be the case that living things can do things that don't violate the laws of physics, but they would never be anticipated by the current laws of physics, because it actually requires systems to learn and acquire the capability to actually make these kinds of transformations.
That is an enormously important concept. I'm not saying it's true, but
Yeah.
if it is true, that is a complete refutation of fundamental reductionism as the only way the world works.
Yes.
That as we call it, like we say things emerge, but what most scientists believe is weak emergence means it looks like emergence, but once you understand the real deep structure, you can see it on a reductive. A classic example is the wetness of water. How can two atoms of hydrogen and one of hydrogen, one of oxygen, these are gases, you bring them together and it feels wet. I mean, that doesn't make any sense. And therefore, there's some magic. Well, there's no magic when you understand the bonding structure and how they work together. You can, in a sense, predict that. You're saying something much bigger than that. That in effect is, we'll talk about later, top-down causation. That things build up in a physical way. It creates something on top, which then has a recursive causality to the
Mhm.
bottom, and that, that's
Yes.
controversial.
It's very controversial. I think the reason that this actually gets into this idea of making information material and tying it to the concept
Yeah,
of
yeah.
objects having a size and time, which we can talk more about. But I think because I originally, early in my career, was very interested in top-down causation. And as you're pointing out, it's controversial because when you look at top-down causation with standard approaches to physics, they appear in, very strict conflict, right? Because if we have causal closure at the microscale, there's no room for top-down causation.
Right.
And assembly theory basically has as sort of one of its fundamental pillars, as far as like a principle that we think that is one that's of interest and worth testing about the nature of living systems and what kind of physics they actually represent, is that the sort of future is bigger than the past, and the past is actually constructing and adding information to the future possibility space. And the way that we make that a material property is to talk about this recursion, this like deep history of these objects as a physical property. And so it resolves the issue of top-down causation, but you basically have to restructure the way that you think about laws of physics.
Yeah, as I was going through your book, and of course I've known of your work prior, it's absolutely stunning to think about that. And again, that doesn't make it right,
That's right.
nor to say that I believe it, but I
Right.
believe it's a stunning idea that really needs to be explored. And we're going to do that in depth. What I'd like to do now, just for a few minutes, is to give a little bit of of an overview of the importance. We're talking about how it really might work, but let's look at a bigger for just a few minutes and look at the importance of this idea, because you say that this new approach will help us in understanding some really fundamental questions: matter to life transition, detecting alien life, designing synthetic life. These are big scientific issues, they're big social issues, and you tie all of that to the theory. We've been talking about the theory, but just give an overview of the importance of what you're saying.
The origin of life and the detection of alien life and design of synthetic life are definitely big questions. I think the significance of them for me is that we're actually undergoing a lot of transitions technologically that we don't understand. So there's all this discussion about AI and is it intelligent, is it alive? And so I think there's some existential trauma that humans are facing right now just because we're like animating the world around us and we actually don't know what it is to be animated matter. So I think that's sort of one implication that's not immediately obvious. But just as far as the questions of the origin of life and alien life, like as long as humans have been asking questions, we've been wondering if we're alone in the universe and where we come from. So I think these are just existential questions that we've been asking as long as we've been capable. And the answers to them, I think, are really potentially transformative about how we think about ourselves in the universe and how we think about the future of life on this planet.
One way you've exemplified this is by changing the normal question, what is life, to a different question, why life?
Yeah.
What is that distinction?
So the question what is life tends to focus on definitions, like you're trying to answer like definitionally what is life. And when I was approaching that question, I was very inspired by Schrodinger's book and others that had thought about it from the physicist's conception of nature. But I always thought that you should have a theory and then derive the features of life. And then when you start thinking about a theory, you have to ask, like, what is it about physics of life that the universe can do that it can't do otherwise? Like, basically, why is life necessary to have a fundamental explanation? And I found that a really fruitful thought exercise to try to ask the question differently about what kinds of fundamental processes and natures or what kind of possibilities are afforded by our universe because life exists that couldn't exist otherwise. And then that would be a window into what the actual fundamental physics of life might be.
Yeah, and that's a bit heretical, isn't it? In the sense that life has a recursive approach to physics, as opposed to life being, the deep question prior to what your approach is, whether life is purely random, accidental product of the universe, or is there some sort of a trophism that life comes out of the universe? But no one has really talked about the other way, that life has a recursive causative effect on physics. Although Paul has talked about
Mhm.
building the purpose of the universe into the universe itself, something that sounds like backward causation, but really isn't in terms of quantum histories and
Yeah,
all of that.
right.
So
Yeah. And when I was working with him as a postdoc, he really got me on this idea of state dependent laws, because there's no, when we talk about the laws of physics, there's the initial condition and this fixed law that's supposed to govern the universe for all time. And one of the paradoxical things about life is actually related to this issue of recursion, that it seems to be that the rules change as a function of the physical substrates or the state of the system. And so, he was really interested in this idea whether the laws could change as a function of state, or if you don't differentiate state and law, what does the system look like? And I've thought about that a lot of different ways over the years, but I think for me, assembly theory is the most natural explanation that maintains features that would be consistent with current physics, but introduce these new properties.
okay, well, we're almost ready to get into assembly theory. I'm not avoiding it. I'm
Oh
gonna
no, it's fine. I'm happy.
I want to set the ambiance and
Yeah.
the impact of it before we discuss it in depth, and we will. I promise you. Now, some say, and you have a good, interesting section in the book, that life doesn't exist.
Yeah.
You quote another closer to truth good friend, Frank Wilczek, that life may not be a natural kind. Natural kind meaning something that's a real joint in nature where things differentiate, but maybe more blurred. That sounds a little awkward too, because life certainly superficially sounds like has its own characteristic and is a natural kind.
The issue is, I think if you're studying life on Earth and you're, known biology, you don't really necessarily have to worry about these things. But I think if you're going out in the universe to look for alien life, you have to assume that life is something that you're looking for. And my perspective on that is it must be something abstract. Like it can't just be the exact molecules that evolved on Earth. And we can talk about, why I think they're not likely to be on other planets, but it should be something that has more of the properties of universal laws, because now we're looking for a regularity that emerges on different planets, just like we understand that gravitation is a regularity that shapes the actual formation of planets. So from my perspective, it was either the question of alien life is solvable and it's some kind of natural kind, but we have yet to identify what that kind is, and it might not conform to any of our previous conceptions, or there is no phenomena to call life. And since I'm interested in the questions of astrobiology, the origin of life, and alien life detection, I felt that I had to take as my first principle that there was some universal thing that we were talking about when we talk about life. And as I said, to approach that question, you have to assume that you don't necessarily know what that is. So just starting from a first principles approach, what is that thing, or why is that thing? If you're flipping the question to why is life?
And that gets you to information.
That's right.
And information flow in systems can potentially be what distinguishes life from non-life. So the way we see it on Earth is through metabolism, reproduction,
Mhm.
and Darwinian evolution. But those things may not be fundamental. Fundamental may be this information flow in systems that potentially could be a way to detect life.
Yeah, and the way it manifests on Earth and the kinds of processes and structures we see on Earth may not themselves be present on other planets. Like I always like to make the joke that like TikTok probably only exists on Earth, and I hope it only exists on Earth, because if that's everywhere in the universe, it's kind of scary. But but there is this idea that there's a lot of things that evolved on Earth, or were selected to exist on Earth, that probably exist nowhere else, just because the possibility space is so huge, and there's a lot of causal contingency in the process to invent novelty. So we see this a lot in the history of inventions or the history of ideas, but also in the history of biological architectures. They're always scaffolding on what came before.
Okay. So once again, information has to be some kind of a fundamental thing, a thing, rather than just a description of other things, which are the real things. Information has a reification, a realness to it.
Mhm.
And also required is that information has to have a causative capacity to it.
Mhm.
Right?
Yes.
And how would that work? How can information have causative capabilities.
So this was always the paradox, and we talked a little bit about this with top-down causation. If you assume that the laws of physics at the lowest scale causally describe everything, then there's no room for any kind of informational pattern, a living thing to actually have any causal efficacy. And so this has traditionally been why people might talk about life as an epiphenomena, and why there's debates about weak or strong emergence. And from my perspective, and this really has emerged from the theory development that we've been working on, I hadn't thought about it this way when I started thinking about information as causal. I went through all of these kind of ways of trying to, the history was like start with state dependent dynamical laws, look at informational patterns in living systems and non-living systems. And I did all of these things. And it really just seemed to me that there really was new physics necessary, because there was no way to merge these two narratives without trying to invent some new concepts. And the concept that I've landed on is what I think is the most promising, is to say that information is really evidence of time. And what I mean is actually a causal time. So it's really interesting to me, if you look at the history of physics, that every new theory of physics has invented a new concept of time. And so, if you have Newtonian physics, you have this concept of clock time, and the universe kind of has, is moving through this external frame that's like keeping track of time. And then you get to the 1800s and we have thermodynamics, and time has an arrow. And then you get to, quantum mechanics, and which actually has kind of a Newtonian sense of time, but special relativity has this simultaneity built in. I don't really think it's time. I think it's more about simultaneity, but that's a concept related to time. And what I think life is hinting at is that there's a causal time, that there's really embedded in objects a history of their causation, and they have different sizes in time depending on how recursively deep they are, as far as how much construction history the universe has to have to make that specific object. And so I don't think the universe can generate anything for free. I think it actually takes causation and time to generate structure. There's no spontaneous fluctuation of complex objects into existence. They have to be constructed over time, and that time becomes a material property.
Yes.
If I talk about something like me, that's 4 billion years of causation bundled up into, a small physical structure. If I erase all that time out of me, then I can recover electrons and elementary particles, because the universe doesn't need any memory to generate those structures. But something like me requires a lot of memory and all of this time embedded in me for me to exist. So that's the physical property that differentiates me. And so if you want to go from the microscale and macro scale, the real structure you're missing in between, when we coarse grain things and talk about emergence, is that there is actually a physical time that has to happen between those structures. And that physical time is a feature of the emergent properties that we observe.
A feature of it, or part of the causation?
Yeah, it is it. I think when we're looking at living things, we're looking at structures that are deep in time.
Okay. So in essence, you now have two fundamental differences in underlying your theory: information as a reified thing, and a distinct notion of time. The two are related, obviously.
Yes.
But you need these two fundamental differences in some form to traditional ways of thinking in physics.
Yes.
Okay. All right. It's very, very clear. We're almost ready to start assembly theory, but I just want to make the point again that you're making a very powerful statement that the origin of life, in a sense, is the unification of where biology and physics are together, and the arrow of causation is not just in one way from physics to biology.
That's right.
Okay, so if I got that, we are ready for assembly theory. And so why don't you begin by just giving an overview of what it is, how it was developed with Lee Cronin and yourself and others, in the most general way, then we'll dig down.
Sure. So we started developing the theory with an interest in solving the origin of life problem in the lab. And so we've talked a little bit in this conversation already about sort of traditional approaches trying to synthesize under prebiotic conditions molecules of life as we know it. But obviously after, that enterprise has been going on for almost 100 years, just thinking about this prebiotic soup model, and we have not yet solved the origin of life. And there's still this huge complexity gap between simple molecules and evolved cellular architectures. And so my colleague Lee Cronin, that originated the ideas of assembly theory as a measurable thing in the lab, was really interested in the problem. If I had a complex chemical mixture, how would I know that it became alive? How would I go in the lab and measure that? And he's interested in this because he's actually trying to build robots in his lab that will do sort of a random search of chemistry instead of putting our agency in and selecting things a priori based on known biological structures, allowing information basically to construct into living systems. And how would we measure that? And so that was actually the problem to be addressed. So I think it's really critically important also to understand that, like, when new theories of physics are developed, they are often developed in the sense that there's an experimental thing we measure or we need to measure and we don't know how to think about it. So, there's the great question, what is life? But if you boil that down to, like, I'm going into the lab, I have this random chemical mixture that is subject to different environmental conditions, and I want to know when it's alive. How do I measure that? Like, that's a different kind of question. And so that's where we started. And the key conjecture of assembly theory is that there is a threshold of complexity above which only evolution and selection, or when information processing becomes a part of a physical architecture, can you construct those complex objects. So standard physics would say, the universe can generate objects of arbitrary complexity for free. They just have very low probability. And this is, what underlines Boltzmann brain arguments and a bunch of other things that we kind of assume in physics. And what we thought was, if you go to Mars and you find a cell phone on Mars, that's evidence of life. And if you find two, that's even better evidence of life. We don't expect those things to fluctuate out of the geochemistry of Mars and just spontaneously form.
And that's the Boltzmann's brain.
That's the Boltzmann brain argument, but put in a biosignature context.
Right.
And so then the question becomes, are there molecules that have that property? Are there molecules that we think can't form spontaneously? And the way to formalize this that became measurable was to think about the number of recursive steps to construct the molecule, and in particular, the minimum number of recursive steps. So the idea is, if you take a molecule, and sometimes for people, molecules are hard to visualize, so they might think of like a Lego castle, and you smash it down to the pieces, and you take two atoms and you stick them together and make a bond, and then you make another bond, and you can reuse parts you've used already, or you put two Lego pieces together and then you can reuse that part. What's the size of the shortest pathway to construct that object? And we actually talk about the structure of that pathway as a physical space called the assembly space. But that size of that pathway can be measured in the lab. And Lee's lab has done a lot of experiments with mass spec, NMR, and infrared, showing that 3 different measuring techniques give highly correlated values for this property we call the assembly index, which is this minimum construction history size. And
so you'll look at different molecules and look for this assembly index by breaking them apart and seeing how many parts there are, how many steps there would need to be, and have a kind of a hurdle or a step function at some point where life has to be involved. And I think what you're saying is that's where, at that point, information creates a top-down causation after that, when you get to a certain number.
Yes. So you're bringing up the idea of the threshold. And so the way that this minimum steps corresponds to a threshold is, we had a conjecture that if you observed objects in high abundance, so they have to have multiple copies of the object, above a certain threshold of this number of steps to construct the object, it would be evidence of life, with the idea that the only way to construct such objects was if you had informational constraints in the system, and in some sense, to be anthropocentric knowledge or information or learning had happened that, like, specific to the construction of that object. And, you can think about it just from probabilistic arguments. Every time you take a step, you're actually creating structure in an exponentially growing space of possibilities. And the universe can't exhaust all of those possibilities, which gets to the why life question. Life is actually the mechanism of, again, being anthropocentric, making choices in this very high dimensional space of possible configurations where not all of them can exist. And so to observe one in high abundance means that there's this entire causal structure behind it that has all of the informational constraints to create that structure. And so, those would be things that might be evidence of what people have traditionally called top-down causation. I would just call it a lineage, or the assembly space is, like constraining it to be constructed there. So, but the assembly space again has this structure across time. So it's kind of flipping the sort of way that we think about it. So one way to think about it is there's a firm boundary in the physical universe above which you require memory and history and information encoded in physical systems in order to construct those objects. They don't happen for free.
And how are you getting the memory? A memory in a
So
molecule?
yeah,
The construction?
the memory is that you actually have to carry the history of those causally contingent steps. So something has to actually keep that constraint embedded in the system for that complex object to persist in time.
And how is that physically instantiated?
So it's the way that we think about it in assembly theory is actually to look at the assembly space of the molecule itself. So traditionally, when we're talking about information in DNA, it's been very paradoxical to talk about, like where's the information content of DNA, right? You can't tell just looking at a sequence of DNA if it has function or meaning in the cell or not. And so we have tried not to look at function or context because they're not actually things that are easy to objectively define. And we look for evidence of function or history by looking at the structure of the molecules that are created, because the conjecture is these things would not exist unless the constraints in their environment existed to generate them. So actually it's kind of inverting this property that, the context, and actually looking at the mirror of it in the physical substrate and saying the physical substrate encodes its own laws for its formation. And you should be able to look at the structure of the physical substrate and the rules of its construction and infer whether it was necessary that there was this sort of long causal chain of objects constraining and recursively constructing other objects in order for that thing to exist.
And the argument is that at the early stage, when it's just a few of these steps, you do not need information.
That's right.
And at the later steps, you need this information, the memory, the back history, the lineage, in order to do that. So
I can explain that a little bit because I think it's not intuitive for everyone, because we don't so one thing is, like, if you think about the structure of the assembly space, and we talk about these sort of nested assembly universes to talk about how big this space is, but if you start stacking objects by their complexity, by their assembly index, there's a sort of clear ordering of how many objects there are at each layer and what kinds of paths you can take through this construction space to get to a specific object. And so if you think about just, simple chemistry, or actually, let's do it with Lego. If you think, if I put a bunch of Lego in a dryer, and actually saw somebody do this experiment on X, and I thought it was and they tagged like assembly theory. It's a great example experiment. You put a bunch of Lego in a dryer and you just let the dryer run. What's your expectation of the object distribution that you're going to get? You might get like a couple pieces of, two Legos stuck together. And you might actually get a few of the same configuration, but the more complex the object, the less likely you are to see it twice, because there's no information or constraints in that system. And so what we see this in chemistry and prebiotic chemistry all the time. If you run a prebiotic chemistry experiment and you don't put the sort of priors of the chemist that knows what product they want and, puts all the right constraints to get that amino acid or that nucleic acid, if you just run an experiment like the Miller-Urey experiment for days on end, you get what's called a tar.
And that was in the 50s, where they threw some chemicals in and threw the equivalent of a lightning bolt or some electricity, because they tried to simulate what would be the early Earth 4 billion years ago or whatever. And they got some amino acids. And so that's a big deal. It
was a big deal. So they stopped the experiment, I think, after a day or two, and they measured what they got out of it was amino acids. And I think everybody at the time was really excited that aliens were going to be, or new life forms were going to be crawling out of the test tube in a couple of weeks. What happened is, if they kept running it, they were just making every possible small molecule, non-complex molecule, because there's no constraints to actually form specific structures and then use those to scaffold to more complex structures, which is what life does. And so what we see is that, and part of the reason that you can't do that is if you imagine you're trying to exhaust all the possibilities, like all the small things, if you start to make slightly more complex things, each layer is exponentially growing. And actually, you don't have the resources to do that. There aren't enough resources in the entire universe to exhaust small molecule chemical space. chemical
So that
speed.
they're exponentially
Yeah,
growing the possibilities. Even a
right.
small molecule can have more possibilities than there are atoms in the whole universe. So,
Yes.
yeah,
And
that's
so
clear.
yeah, so what we see is that if you think about it as sort of a random walk and you're just making structure, like there's no way of getting complex structures in high abundance unless that whole space gets collapsed to make some structures, because there's information in the system constraining the set of possibilities to create those and make them in high abundance. So if you see a complex structure like a human being, a cell phone, a DNA molecule, and you see it in high abundance, it's surefire evidence of life, because it suggests there had to be a regularity in the environment, a law-like process that was selected to construct that object.
So, do you have in the theory, is it a smooth transition or is it a step function dramatic transition? Because we're talking about no information being required for simple combinations and accretions. But once you get higher, you need this. And what you say is needed is a fundamental
Mhm.
law of the universe, as fundamental as anything we know, that you're adding to our toolbox of ideas.
Yeah.
So does that occur at a step function, or is that smoothly sort of beginning in some ways and then and gradually increasing?
So our current thinking is it's a step function, and I've been working on a paper with Lee and then one of my PhD students, trying to actually understand a phase transition between the sort of two dynamical regimes in assembly theory. One is where you just get sort of this exploration that's undirected, and the other one where you're building these trajectories of complex materials. And I think that is a very abrupt transition. And in fact, we have empirical data to support its abrupt transition. So when I was introducing the idea of the measurement of assembly theory, and I said that we went and, we wanted to go in the lab and measure whether it was life or not. And we, correlated, like we figured out how to measure this property with, a mass spec. So what we actually did, and this was Lee's lab that did this, was they went in the lab and they tried to measure this assembly index for molecules produced by abiotic systems, fossilized materials, meteorites, living things. And they did see a hard boundary where above about 15 steps, you only saw structures that were produced in the living samples. So none of the non-living samples, or the abiotic, or even the meteorites, which are supposed to be some of the most complex materials in the solar system as far as the complex chemistry that they create. Their complexity is they have lots of different kinds of molecules, not that they have complex molecules in high abundance. And assembly theory and this sort of empirical approach we have of measuring it was able to differentiate that. So we have this sort of empirical result of a life detection experiment that confirms that the principles of the theory work for the data sets that we studied. And it's very abrupt at 15. I don't think 15 is a universal number. I think it's very specific to the assembly space for covalently bonded chemistry of schnapps as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, which form the foundation of the chemistry of life on Earth. And that what we think is any material, whether it's minerals, memes, other substances. This is very, very provocative idea. Any material will have an origin of life boundary above which you would say that there had to be information to construct these particular structures.
Look, that makes sense that what we see on Earth, if it is a step function at 15 or whatever the number is, that could be different with a different set of chemical elements of which you are constructing. That makes entire sense. But what is clear, and we're saying it a couple of times, but I really want to emphasize it, is that what's lying below both of those, the 15 on Earth or the 17 or the 3 or the 100 on some other place, are driven by some very fundamental law of the universe that is the equivalent of the four forces of physics. I mean, it has to be some very fundamental idea that we're adding to it.
Mm-hmm. Yes. So the way that I think about it is the space of possibilities that the universe can construct is far too large for everything to exist. And in some sense, life is the mechanism of what gets to exist as far as like what gets selected from this huge possibility space to be constructed. And when this happens, it emerges along these causally contingent trajectories. So basically, the universe has to make, I don't like the word choices, but it like selection. It has to select based on the structures that exist, what gets to exist next, and carves out these trajectories through. And if you're on a complex planet like ours, where a biosphere and a technosphere have emerged, we're basically growing into an exponentially expanding space. And this is why our biosphere looks more and more informational, because it's getting deeper and deeper in time. And so all of this history and contingency and recursion in the construction process basically gets folded up into the current physical structures. And so the things that exist on a living planet are getting deeper and deeper in time, even though we only see them in these sort of small physical packages. And so one way I talk about it in the book, which I didn't get into a lot of detail about, is that the virtualization of reality is just really a manifestation of the fact that living structures are getting deeper and deeper in time. So more of the sort of things that we're interacting with in our environment are actually, like their physical structure is in information in time, not in the physical three-dimensional space that we're walking around in.
But it's exploring this phase space of possibilities, yes. Hyper exponential.
Right. Yeah. And so, we're familiar with the idea of the expanding universe. And when we get really provocative about assembly theory, we just say like time is the mechanism of the expansion. The universe is getting bigger because time is actually increasing and time is actually expanding the size of the universe. And you might see that in terms of like the spatial grid of the universe expanding. And on a planet that's in this combinatorial space, you see it in terms of the combinatorial space and the way that it's expanding as it moves into it. And so I think that's pretty provocative, but I think this idea of time as a generating mechanism in life is, and it's a causal time, is pretty profound and very deep, and also very explanatory of a lot of things that we haven't had a common language to talk about. So going back to the hard problems you mentioned before, a lot of the ways that you could talk about the three hard problems, matter, consciousness, and life is life is this sort of construction process building into the space of possibilities. What we see as material right now, electrons and things are actually like when you move the time out of it, but there's this sort of extra dimensionality that makes things like us material, but the material property is now embedded in time or this causal structure. And when things get very deep like us, they have a lot of internal informational architecture in this other space that maybe our sensory perception is not as aware of. And I think that's where conscious experience is actually the fact that we are temporal. It like time is a material in us, or information is a material in us.
Okay, so that's a much bigger question that we're dealing with. So maybe we'll get that to a little later.
Yeah, there's a lot of stuff rolled up.
That's good. And your argument is that they all can be solved simultaneously. They're not just similar kinds of problems, but they really have some underlying fundamental connections. I mean, so it's entirely valid to talk about it from that perspective. Whether that's true or not is a different question. All right, this is the perfect place to describe how assembly theory articulates with other similar kinds of ideas. And I think that'll give us a richer understanding of assembly theory. And I'm going to start with our good friend, Stu Kaufman, who says that reductionism stops at the watershed of life, his famous phrase, and that life is the terminus of a physics worldview. He talks about affordances, which is similar to your probability spaces. So how does assembly theory articulate with Stu's self-organization, autocatalytic sets? He proposes that the self-organization and the emergence of autocatalytic sets of polymers, specifically peptides, are responsible for the origin of molecular reproduction.
Yes. So I'm a huge fan of Stu's. When I was a PhD student, I was carrying around the origins of order all the time. So I was really influenced by his ideas early on. I think I really like the idea of the adjacent possible. And I think that's very natural in assembly theory, because the way we talk about the construction of this possibility space, there's always a neighborhood of things that you can access given a certain construction history and a certain sort of location in time is a way I would think about it. There's also an adjacent impossible in assembly theory, which I don't think Stu's he's, sort of talked about in his work, but I really like this kind of play on the idea, which is, this possibility space is so large that there are actually things that are moving away from us exponentially that we will never be able to construct in our biosphere because the history is going in a different direction. And so I think the fundamental difference between our conception and what Stu's worked on is this idea of information and time being physical and restructuring the laws of physics. And I think he's kind of saying that there are no laws because there's an assumption that the laws must look Newtonian. And I don't think that the laws need to look like initial condition and fixed law of motion. I think there's other kinds of laws we could discover that would just...
Does that articulate with your claim that assembly theory can prove that Boltzmann's brains not only are highly unlikely, but if in an infinite world, highly unlikely means it'll happen an infinite number of times?
Yeah, no, I think they're impossible. So, and I think one of the things, you've been doing right to hold the ideas to the fire, saying, like, well, these are very provocative ideas and they'd be great, like really interesting if true, but like we don't know they're true. And these are things that we're really thinking about experimental tests. And I think there are some experiments you could design to test that where for specific kinds of experimental boundary conditions and complex objects, you can show that there's actually a minimal time for them to spontaneously assemble. But this is a hard experiment to do, but I think there is a construction bound in our universe that for any object, there really is a minimal clock time for it to exist.
Okay, so now some other theories on the phase space you're talking about. You're familiar with George Ellis's possibility spaces?
Yeah.
It seems very similar.
Yeah. So I am such a fan of George also. You're doing like my favorite hits of like people that have influenced me. I think that's very, very related. And also to his conceptions of top-down causation. I mean, he was always very adamant about information being a causal category. And I think what assembly theory allows is sort of a way of giving that possibility space a physicality that you can go and measure in the lab. And that's been the main thing that we've been trying to do is like, if you have a measurement, you can go and test the consequences of these ideas. And so I'm hopeful that some of the things that have been traditionally philosophical questions will actually now be able to go and test. And that's exactly what we're trying to do.
Okay. It's a very high ambition and a very worthy one. Next, and we'll do these quickly, David Deutsch's constructor theory.
Also a huge fan of that one. And Chiara Merletto, obviously, I'm a huge fan of her work too. So I think constructor theory deals with what's possible and impossible and why it's impossible. So I kind of think of constructor theory as very similar to assembly theory, but not accounting for the structure of time, because constructor theory is usually in a timeless universe. And there are some things where, you have to have a forward construction process and a backward construction process. And like both constructors have to exist in order for the process to be reversible, which is something Chiara's worked on. And assembly theory has, like if you think about these operations of building objects, these joining things we do to construct the assembly space, they're construction operations, and you need a physical structure to exist to cause that transformation, which sounds very constructor theoretic. So we kind of think we have this concept of assembly possible, which is if you think about all the possible trajectories that you could have sort of unconstrained by history through an assembly space, I think constructor theory lives there. And I think it actually defines the boundary of that space. And assembly theory is more specific to the kinds of histories that get built within that space and what kind of laws actually get physically embedded.
Very clear articulation between them. Now we go a little bit further afield. Gregory Chaitin's algorithmic information theory, which he applies to defining life, origin, and evolution.
Yeah, so Greg also has this really nice idea of like busy beavers and open-ended complexity. So algorithmic information theory, I think, is a wonderful theory about trying to quantify complexity, but I think there's many differences between what we do in assembly theory and what AIT talks about. So AIT talks about sort of program size complexity and minimum description length. And assembly theory is there's physical constraints on constructing physical architectures. And we also talk about a minimal construction history, but that minimum construction history doesn't need to correspond to a description of the system. It's actually a physical measurement of something intrinsic to the system. So I think AIT is very observer focused and assembly theory is very physical, what you can go and measure in the lab focused. And they actually end up with very different conceptions of what's complex. So algorithmic information theory has a conception of very random structures being the most complex and unpredictable. And assembly theory says those things are actually really hard for the universe to construct. So it tends to use much more recursion. And I actually think randomness in nature as an evidence of intelligence, because it's only be able to produce once intelligent things discover computational laws, because they can describe randomness in a way, but that's a whole nother thing. So I think computational complexity theory actually sits pretty late in the evolution of a biosphere, and assembly theory has similar sort of structure to some of the principles, but radically departs in a lot of the other implications of what the theory would say about the physical nature of reality and how we can think about it. So like this idea of time being physical and all these other things you couldn't get out of AI.
Right, for sure. Yeah, there is certainly a big difference. You have a assembly there has a real world physicality to it, as opposed to a conceptual abstract definition.
Yeah. And I do
Algorithm.
talk about this in the book. Like, if you look at the past unifications in physics, it's like, we had celestial and terrestrial motion, or space and time, or particle and wave. And every time that we unify these concepts that seem different, there's like a really different conception that emerges that's neither of those things, but might have, echoes in them. And I think matter and computation have been thought of as different. So, the sort of algorithmic information theory sits firmly in the computation in an abstract world, and matter is really physical. And I think assembly theory is a marriage of the two, but it says fundamentally different things than either of those theories say separately.
Yeah, agree.
Yeah.
Agree. Okay, two more that are again a little bit further afield. Ed Friedkin's cellular automata, self-replicating simple elements, and then similar but not the same is Stephen Wolfram's rules, new kind of science, that certain kinds of rules underlie all of reality and build the physics and the biology.
Yeah, so these I kind of see as a marriage of standard physics and computation. And so, cellular automata are often built on an initial condition and fixed law of motion, and people are looking for emergent patterns to explain complexity. And I just don't think that's explanatory enough. And then when you get to Stephen's ideas about this sort of hypergraph and all rules exist everywhere, that sounds a lot like the multiverse to me, and it doesn't really explain the rules we have here. And it's another mathematical description that you can provide for the laws of physics as we know it, but it doesn't allow you to really anticipate these kind of other principles that we're talking about in assembly theory. And again, it goes back to working from the science of measurement and actually being in the lab trying to ask a fundamental question about the way reality works. A lot of these other approaches are, not making that bridge. And if you look at the history of physics, that's where all of the major things were. Somebody was in the lab taking measurements, trying to answer a fundamental question, and those measurements radically reshaped the way we think about things. Like, my favorite one is like Einstein taking seriously that speed of light was a constant because it was measured in the lab to be that, and everybody else was still ready to think the measurements were wrong. So I think this idea of embedding our abstractions in what we can physically go and validate is really important, because that's actually when we get the really counterintuitive ones that end up being broadly explanatory. So I could say, the universe is a computation, all computations exist somewhere, but I don't think that really helps me understand the evolution of life on this planet. And that's a question I'm interested in.
All right, this has been great, Sarah. We can talk about this for a long time, and I'm sure we will again. But I want to spend a little time on what you've mentioned a couple of times in passing, but I really want to focus on it now, which is the hard problem of consciousness, a fundamental question that Closer to Truth deals with. How can physical brain states produce mental states which seem to have a non-physical character to them in one way or another? So how can assembly theory help, or can it help elucidating or reframing the hard problem of consciousness?
Yeah, so the way I posed it in the book, and the way I've thought, just trying to think about hard problem of consciousness, hard problem of matter, and hard problem of life in the same space, is to think more about, again, this question, like, why consciousness? Is there some things that can only exist in the universe because there are conscious entities to mediate their existence? And so the example I give is this idea of rockets, which, existed as informational patterns in human brains for centuries before they were constructed. And obviously we had to develop a lot of technology. So there's this kind of interesting thing that I think conscious agents can do, which is actually take informational things that seem abstract, and make them physical objects in our environment. And even, nowadays, like, pretty much everything in your environment or my environment is the product of a human mind. It's kind of crazy to think about, like, looking around a room and say, like, these were all ideas in someone's head before they were built. And so that, I think, is very non-trivial and needs to be taken seriously as a feature of our reality. And what assembly theory would say about it is, if you take seriously that objects that are generated by evolution, or, like, by this assembly process, the assembly space, get deeper and deeper in time, things that are very deep in time have this massive combinatorial compositional, like causal assembly space that is their physical structure, and recombinations of that space actually allow new things to be structured. So it gives this idea of having a past that's getting larger with more complex objects, and that past is actually combinatorially constructing the future. So if you have a very deep assembly space, a high assembly index, it means the future horizon for that object is actually very large. And I think there's some feature of consciousness about the relative sizes of those two horizons that makes us very unique as creative agents in the universe. That we actually have this sort of counterfactual space that's actually existing in the temporal structure of any one of our minds that we
So
are.
that seems like a critical mass argument for
Yeah.
consciousness, which is classically, an atomic bomb. You have two pieces of U-235 or plutonium, and they're both a little radioactive, and they do nothing. You put them together, and you have an explosion. And so that's the critical mass. And so that's what you're saying in terms of the explorations of the combinatorial space, that at some point there, consciousness can emerge. I'm not sure
So
that.
I think that I think I should clarify, because I don't think that consciousness is unique to us. So I think other evolved entities can have it, but I don't think it's a property of fundamental particles.
So therefore, you're not a panpsychist.
Yeah. So I think, but I think if you want to explain anything, you can't take that thing as fundamental. You have to have that thing, be a consequence of some fundamental structure you derive it from. So if you're interested in explaining consciousness, I don't think you can take it as fundamental. I think you have to take some structure consciousness is made out of as fundamental. And I think that structure is actually also what I'm arguing that life is made out of, which is this idea of taking causation and time embedded in objects very seriously. And living things are part of that structure. And there are, for things that, as I said, are like very deep in these recursive stacks, and there's a lot of recursive history packed into a very small volume of space, like the architecture of a human brain, there is a level of experience to that you wouldn't see in objects that are not that recursively stacked.
And so that same way of thinking underlies both the origin of life and the origin of consciousness.
That's right. And I think other organisms, like I said, can be conscious, but I also really agree with David Deutsch's conception of this idea of universal explainers. And there's something fundamentally different about the architecture of our minds relative to other organisms that have emerged on our planet. And I think this has to do with the size of the horizon and what we can potentially explain through our conscious experience and how we navigate sort of the future possibility space because of that. So I think there is, I think there's some additional level shift of some variety with architectures like us, but I have yet to really think through exactly what that looks like to me from an assembly theory perspective.
You're allowed to take more time in your career.
Yeah, thank you.
It all doesn't have to be solved today. We'll give you.
I've been thinking about this one for a long time too, but I know we all have, so it's fine. It's good.
Right.
I'm just going to work on the origin of life first, and then maybe
Okay.
I'll
All right. We'll
solve that one.
We'll follow you. So, two questions to relate now to artificial intelligence, AI, a hot topic, obviously. The first is, it would seem that your critical mass argument for consciousness emerging as not being fundamental, emerging from life, relationship with time, information, relationship with time, over explorations, further explaining the explanation, would make it a prima facie argument that AI consciousness is a given. The question is when it will explore that space.
Yeah, I actually think AI systems are pretty flat in terms of their causal structure right now. What I mean by that is, I think there's a fundamental confusion that a lot of people think that life is about prediction, and predicting the future is the fundamental thing that life does. And I think life is actually about constructing the future. It's a much more active, like physical structure. And so AI algorithms are trained on huge volumes of patterns, and they can predict features of those patterns, but it doesn't mean that they're actually actively constructing their patterns. They're responding in kind of a way to an environmental stimuli to try to predict them. So, and this gets into the ideas of like, is AI creative or not? When you have an evolving lineage and you get to something intelligent like us, we can put our intelligence in pretty much everything in our environment and sort of animate it at a certain capacity. But the causal structure underlying it, and like whether it retains the features under that kind of, lineage is another question. And so I tend to think about the interesting things about AI are not putting the intelligence in a box, but how are these intelligent animated technologies that we're interacting with, like what kind of global structures are we emerging that might be more alive than we are even. And I don't know exactly what that looks like. And I don't, so I don't know that I would say that they have, we're at any position to say that they have conscious properties or not. And I don't think this idea of being able to predict language with high accuracy is a sufficient
for sure.
bar. And in assembly theory, it's super interesting because the past is deterministic, but the future isn't. It's non-determined because the space is getting larger. And I think what we have oftentimes with the laws of physics is we're predicting the past, but we don't really have a way of understanding the novelty that gets generated in the present. And I think AI is very good at predicting past structures, but they can't anticipate necessarily the future because they're not constructing it. So they are in symbiosis maybe with humans, but yeah.
Okay, so just to articulate some very specific things, but in principle, AI should be able to become conscious.
Yes, I don't see any reason that any physical like material with enough ability to have a recursive depth in its like physical architecture couldn't be conscious.
Okay.
The question is whether that's possible in silicon or not, and what would that architecture look like.
Yeah, and that's.
And so I'm more likely to think that AI will be engineered in chemistry before it will be actually possible in silicon.
Okay, well that's fine. That doesn't change the in principle.
No, yeah, but in principle, yes, I totally think that.
Yeah, and also the question of creating. You tie together creation with the consciousness, and it would seem that zombie AI without consciousness can create. Or you're saying no?
I think the question is what is novelty and how does the universe generate it? And so and this is a fundamental question that, we're going back and forth quite a lot about in assembly theory, because we basically, at the base, in some sense, I think the universe is completely non-deterministic. And I think quantum mechanics is strong evidence for this. And I think determinism emerges because you have all these causal constraints along lineages. And once you get into this possibility space and you collapsed it on, a very small part of like this huge possibility space exists as physical objects, it becomes more and more deterministic. And so I think this issue of like the non-determinism as being the background in generating novelty by, some of that structure is not constrained, is a really hard question, because you basically have to account for what the universe already knows in some sense and what's new. And I don't know that we have enough evidence to say AI are generating things beyond what humans are generating. I think they're generating things that are in a space that humans could generate. It's just the possibility space is too large for any one human to do it. So we're making AI agents that can basically fill this space of structures that we could create. Whereas if I look at the history of Earth, it's very clear that humans did things that were not possible before us. And so I don't preclude the possibility that AI could generate fundamentally new processes, kinds of structures in the universe. But I think it's too premature to say that they've done that already.
Well, one thing seems sure, that with your conception of assembly theory, as it applies broadly, not just to life but to mind, that free will is not an illusion.
No, not at all. It's a real physical property. And this gets into the interplay of the determinism, right? Like free will requires both. And so I think like people are either the universe is deterministic or it's random. And you need something in between in order to allow something to have the freedom to make choices, but also the will and the causation to actually enact them. And I think assembly theory also, plays into some nice features of free will, which is free will is often something that you can't do instantaneously, because you can't violate the laws of physics. So I always like to give the example, like, I couldn't be in New York this instant having this conversation with you. I'd have to plan ahead and get on a plane. So it's within my causal horizon of things I could do in the future. I have free will to plan that, but I couldn't make it happen instantaneously. So I think there's definitely room for free will in sort of this space of this combinatorial future and what constraints the present can put on it. Yeah. And agents like us have that capability.
Yeah, the argument you gave could be built into the laws of physics, initial conditions, and just running the movie forward. People who say there is no real free will would not accept the argument that you could.
I think that's not, but that's not actually explanatory, right? Like that just explains. So, I Sean Carroll gave me this example why no new physics is needed, of like taking a screwdriver, rewinding it back in time, getting the initial condition and winding it forward and recovering the screwdriver. But the initial condition was the screwdriver. It wasn't the initial condition in the universe, because you started with the screwdriver to specify the initial condition. And so, of course, you can say the initial condition allows you to execute the actions, but it's not explanatory because to specify the initial condition, you had to say I was doing those things.
Yeah, no, good. So would it be fair to say that free will, the real free will, libertarian, as we say, you could have done something else, coming out of assembly theory, is the product of information being fundamental, the nature of time and its historical lineage, and the hyper exponential growth of the possibility space or assembly space.
Yeah, and I also think there's an additional mechanism at play here that gets back to the why life, or you might ask, why free will? Why would the universe construct things like us that seem to have independent agency of each other? And I think, I have this real strong sense that life is the mechanism of what gets to exist, and why is like one of the most fundamental ways I say it. It's like the mechanism of selection of what gets to exist. And I can think, like, if you and I can make different choices, the universe is actually kind of maximizing the size of its future horizon of what it can generate. And then obviously, like, we're all kind of in this space trying to construct the future. And so it is in some sense a way of maximizing. I don't like entropy. I don't really think entropy is fundamental, but people are more familiar with it, like maximizing the entropy over future possibilities by allowing structures like us to have causation and also have some freedom about what kind of causation we want to be.
Is there a teleology built into the universe as you've described it?
Well, I think, this is such an interesting question. I love thinking about it. I think yes, and I think any kind of fundamental physics that would describe life has some kind of teleology, right? Because you're talking about the emergence of goal-directed and purposeful systems. And so I think the structure underlying that physics has to have some of that, but I see it much more as a consequence of the physics, not the fundamental feature that gives rise to the physics. So teleology emerges along lineages, and you get purposeful agents like us that choose to do things in the world and talk about purpose, but that's something that the universe constructed itself into.
Sara, this has been absolutely terrific. I thoroughly enjoy it. I now understand assembly theory better and its implications. I'm not sure I'm an acolyte quite yet, but maybe I'm along the path. So what I want to do now is ask a series of very short questions, but I want your answer to be really short. These really don't count for anything. So you're free to change your mind in the future or denounce what you say here. So let me just throw them at you and see what you say. First, are the laws of physics immutable, or can they change?
They can change.
The laws of physics, are they necessary, chance, or brute fact?
Necessary.
Okay. So they are necessary and they can change.
Mm-hmm.
Okay. Is the universe fine-tuned for life and mind?
I think it appears that way because of where we exist in time.
Okay, so that's but it doesn't have to be that way. It's just an accident to where we are. Like we can see.
No, I think it's pretty intrinsic. I guess I would say that, yeah, we live in a living universe.
Okay, all right. Well, that's a stronger position.
Yeah.
So I think you may have answered my next question, but is life a happy accident, or is life somehow built into the ultimate laws of physics?
Ultimate laws of physics.
Okay, very strong position. All right, different question. Let's assume order of magnitude 10 to the 22nd to 10 to the 24th, order of magnitude number of stars in the observable universe, and at least that many planets, not necessarily, obviously not all in the very small percentage of those in the habitable zone, but huge numbers. So in the cosmos, 3 quick questions. How prevalent is simple life?
I don't know.
Simple life, as you would define it, as no one knows it. In other words, not.
No, I don't know. Like, I literally don't know. I haven't computed it yet from an assembly theoretic principle. But
is it possible to compute from assembly?
I think so. Yeah. Yeah.
Okay.
I think if we get the theory right and we do the experiment right, we will be able to definitively answer that probability in the same sense that we talk about other fundamental, like the distribution of baryonic matter in the universe or something.
Wow. Okay,
Yeah.
that's a big claim. So we'll follow you, and
That's what that would be the aspiration of a scientific enterprise, right? So
right. That would be the goal of a whole scientific era.
yes.
And then going on from there, maybe this is irrelevant now, but how prevalent would intelligent life be if there is simple life? Maybe a percentage of that, and then from there to technological life. So this is sort of a sequential question.
Yeah. So again, I don't feel equipped to answer this question yet. Like, I think, I could obviously answer with like my optimistic bias about what I think these probabilities are, but, I'm here trying to answer these questions rigorously. So I have to maintain that there may be nothing out there, or it might be very prevalent. So I actually, Paul was really great and like really trying to ingrain that in me, that like, we don't know the answer to this question, and people are often ready to jump the gun and answer it. So that's one of the reasons that I'm just like, I can be really sure about some of the previous questions, which might be harder because those are stances on how I build a theory,
Right,
but the consequence of it.
right.
And, that's something that we have to test. But my intuition is that, if life forms on a planet, it is about this open-ended cascade of complexification. So I think most biospheres would emerge into something we might call intelligence or technology, but it would potentially radically different than here. I think there's some points that could stop, but I think most of them would. I think it's pretty open-ended.
Well, that's a big claim, because many people that I've talked to say the exact opposite of that. That simple life is very, very prevalent, but intelligent life is extremely rare. In fact, we may be the only one, because the great filter, as they say, in the Fermi paradox, which is the next question, is between simple life and intelligence.
Yeah, I think the hard step is the origin of life.
Okay, that's a big claim, and an important one. Your answer to the Fermi paradox, I'm not even sure that's relevant after what we've said, but the vast universe as extraterrestrial intelligent life, where are they? If there's so much, we don't see any of them.
Right. So I wrote about this also in the book, about this idea of a great perceptual filter, kind of playing on Robin Hansen's idea of the great filter, which is the idea that, our theories and our technology have to evolve together, and our understanding of the world evolves with our technologies of perception. So, for example, we didn't know about microbes on our planet until we invented microscopes, right? So in our past lineage, of course, like we had some knowledge, we were microbes in the past. I don't know what that knowledge would have looked like, but over billions of years, we evolved into humans, and then we had to invent telescopes to actually see that. And I like the analogy of gravitational waves, because it's very clear about the relationship between theories and being able to see the world and build the technology to see the world. So Einstein, came up with the idea of gravitational waves 100 years before we had the technology to detect them. And I think alien life is really similar. I think we literally don't have the explanatory paradigm to have the technology to actually know what we're looking for. And that's really what we're trying to do with this kind of merger of theory and experiment, to solve the origin of life problem.
Right. So the question that many people ask, that I ask, how long do we think it'll take to discover extraterrestrial life of any kind through the spectra of planets passing in front of their host star, or finding some artifact that some people are looking for, some approach? I think your approach is those things, fine, do it. But the best way to do it is theoretically, through assembly theory, to see what the predictions would be from the theory, in order to do that. So the question, how long will it take for us to be sure? How would you answer that? I don't want to answer it for you.
Yeah, no. I'm very inspired by my cosmologist roots and trying to understand like things way out there or deep in the past of our universe by doing experiments here on Earth, right? That's the sort of combination of particle physics experiments and cosmology. And this is one of the reasons that we understand the large scale structure of the universe so well. And so I think the problem of alien life detection is we don't know what we're looking for, and we don't know how frequent life is. And so if you build a theory for life that you can go and test in the lab, and you have a series of experiments that are trying to basically de novo originate alien life, a different chemistry from life as we know it in the lab, you're testing that theory and validating it experimentally. And if it's universal physics, it should apply to these other planetary bodies. So I think our best shot of detecting alien life is actually to go through this paradigm shift of treating the problem as a theory experiment one and solving it. Now, the question of how long that takes, I don't know. So I like the analogy of Super Kamiokande, which has, an unknown physical mechanism it's looking for, which is the decay of the proton. But and so they have these vast volumes of water, and they're looking for this decay event. And the longer they don't observe it, the more they bound our theories that allow proton decay. And so the origin of life is a little different. We know it happened once in our universe, so we know it's physically possible. But if we build the experiment, and we don't observe events of like a planet simulator simulating planetary chemistry in a lab over 100 years, we know that it's not common. So I think we need to really think about not just validating the origin of life as, like proving the mechanism, but also constraining the likelihood by this kind of random search.
Okay, last couple of questions, close to the truth favorites. What exists, by which we mean what are the minimum fundamental categories that are not reducible to anything else?
Causation and time, I think, for me right now, but only because I'm trying to describe life. So I think if I was doing a different part of physical reality, I would say something different.
And information?
Mm-hmm. Yeah. So to me, yes. So it's causation and time, like causal time. But to me, the way that we see that in the physical world is information. We call that thing information.
Okay.
But there's an underlying physicality to it, and it is really the substrate of what has generated us.
And the most fundamental question, our favorite, why is there something rather than nothing? Because you have information. Where did that come from?
Yeah, so this is hard. And the way that I think about addressing that problem is assembly theory does not start with an initial condition and a law of motion. It starts from what exists now, and it works backwards to construct the assembly space, and then you can build a future horizon. So you're always just kind of talking about the local existence bubble of this structure that exists in the present moment as what exists. And so why anything exists is a much harder problem, but I think what it tells you is within the space of all possible things that could exist, like how much selection and causation is in this structure that actually does exist.
Yeah, but that's a different question.
It is a different question. And I think it's one you can actually answer. I don't think the question of why something exists rather than nothing. Nothing is a concept that exists in the physical universe. And, people talk about the multiverse and all these other universes. And I always think that's a structure that exists in our physical universe.
Yeah,
I actually don't. I think we should take seriously that the things that we talk about existing out there actually have an existence here, but their existence here and the way is different. It's like Santa Claus is a good example. Like Santa Claus is an imaginary character, but Santa Claus exists as a cultural phenomena that has real causation. The multiverse to me is an imaginary character, because we don't have access to it, but it does physically exist in how we reason about counterfactuals, about our laws of physics and reality, and it shapes the way that physicists interact with the world. And so I have this sort of conception that everything that can exist actually does exist. It exists in a real physical universe. And when we talk about these counterfactual things, it's actually part of the universe's mechanism of generating more existence because it allows us to be creative and construct things. It's a very physical sense.
And fill out the possibility space.
Yes, that's right. So these ideas don't exist until we think of them, and then they can become physical realities. But the way they become physical is not always the way we talk about them or the way we visualize them in our mental architecture.
Many thanks, Sarah. It's been terrific. Life as No One Knows It. I recommend it highly. A visionary book. You will learn a lot for sure. May not agree with everything, but it certainly will enrich your understanding of reality. Viewers who like Closer to Truth can make a tax-deductible donation to Closer to Truth by clicking on the donate button below. Donations directly support the creation of videos like this one and ensure we can keep Closer to Truth free from paywalls. Viewers can watch more than 100 Closer to Truth TV episodes and more than 1,500 exclusive videos on cosmology, fundamental physics, life, astrobiology, and related topics, including with Paul Davies and Marcelo Gleisa, and now with Sara Walker on the Closer to Truth website and the Closer to Truth YouTube channel. Thanks, everyone, for watching. Thank you for watching. If you like this video, please like and comment below. You can support Closer to Truth by subscribing.